not pay attention in this particular topic, and you shall not pass!
Hello and welcome. Today we're going to be starting a new topic, electric circuits, and your first lesson is electrical charges. Your key learning points for today are: outline the effects of charged objects, apply knowledge of atoms to infer how materials can become positively or negatively charged, analyze experiments with static electricity, and explain how a Van de Graaff generator makes your hair stand up. Let's see what you already know. Number 1. Draw a diagram of an atom and label a proton, neutron and an electron. Number 2. State the relative charges of a proton, neutron and electron. Number 3. Explain why atoms seem to not carry a charge when they are made up of particles that do carry a charge. Pause now, have a go at these questions. When you're ready to move on, press play. Let's see how you did. So, atoms are made of protons, neutrons and electrons, and they are arranged something like this. The protons and the neutrons are in the middle, and the electrons are on the outside. You may not have drawn your diagram in a three-dimensional way like you can see here. You may have done your electrons in orbitals around the outside of the nucleus. That's fine. Next, the charges. Protons have a positive or a +1 charge. Electrons have a negative or a -1 charge. Neutrons have no charge. They have 0 charge. Finally, why do atoms appear to be neutral if they have particles that contain charges? Well, in atoms the number of protons is equal to the number of electrons. This means that most atoms have a total charge of 0. In other words, all those pluses and minuses cancel each other out. So on to the new information. What is static electricity? Let's start with a little bit of history. In ancient Greece, it was known that if you rubbed amber with cloth, that amber could pick up small objects and dust without even touching them. The word electricity is derived from the Latin electricus, which means like amber, from the Greek word for amber, electron. Static electricity occurs when there is a buildup of electric charge on the surface of a material. It is called static electricity because the charges don't move. Here's an example of where you might have heard the word static before. This is a regular caravan. This caravan can move. This is a static caravan. The static caravan doesn't move. We're going to take a look now at charging by friction, which is one way that you can make something have static electricity. Static electricity is caused when certain materials are rubbed against each other. Electrons can be rubbed off one material and onto the other. The material that has got the extra electrons is now negatively charged. The material which has lost electrons is positively charged. How do charges behave? Well, in exactly the same thing happens with charges as happens with magnets in terms of what happens when you hold them close to each other. Remember, a north pole and a north pole of a magnet will repel, and a north and a south will attract. In the same way, a positive and a minus, negative, will attract. A positive charge and a positive charge will repel, and a minus charge and a minus charge will repel. Attraction occurs between particles with opposite charges. Repulsion occurs between particles with the same charge. Now we're going to take a look at a demonstration where I will show you how we can prove this to be the case. Okay, so now we're going to take a look at charging by friction. Now, some insulators become charged when you rub them with another insulator, such as a dry cloth, for example. So this is going to be my dry cloth, and then the electrons are transferred either from the cloth to the insulator or vice versa, depending on what the insulator is. Okay, so we're going to use two insulators here. This is my polythene rod and this is my perspex rod. Now, in theory, if I was to rub this polythene rod with the cloth, I should have a transfer of electrons from the cloth to the polythene rod. So let's try and charge up the polythene rod. Okay, now we've charged up the polythene rod, we're going to mount it on this little holder here. Okay, and you'll see why in a moment. Okay, so in theory, the polythene rod should have a negative charge associated with this end, the end where I did all the rubbing. Okay, so now I'm going to get another polythene rod and I'm going to do the same thing. Okay, so in theory, I should have a negative charge here and a negative charge there. What happens when you put like charges together? They repel. So I can force the rod to rotate by holding a like charge close to it. Now, the opposite is true if I was to try and do the same thing with the perspex. So the perspex, instead of having electrons transferred from the cloth to it, then we have the electrons transferred from it to the cloth, making the cloth negative and the perspex positive. Let's see if that makes a difference. So in theory now, I should have a positive perspex rod and a negative polythene rod. So let's see if that makes a difference. Remember before it repelled, this time it attracts. Let's make sure it's not a fluke. Put it that way. See if I can put the brakes on. Yeah, and pull it back this way. Okay, so what I essentially have is I have a hanging polythene rod. Okay, so that is hanging like that. Okay, and if I was to bring in the polythene rod, by the way, we've already given it a negative charge, if you remember. So if we pop some negative charges all the way around the outside. Remember, I only charged one end really, so I'm just going to draw them on the one end. Now, if I was to bring in another polythene rod, okay, so I'll bring it in from, let's say, this angle. That's the worst three-dimensional polythene rod I've ever drawn, but there you go. And this one also has negative charges around the outside. We have a negative charge, and we add that to another negative charge, and we have a repulsion. Okay, so a negative and a negative, they repel. The alternative of that, or the alternative to that, is if I have the same rod, and this time instead of bringing in another polythene rod, I bring in a perspex rod. So this time, there we go. That's still a terrible three-dimensional drawing. So here we have negatives as before. And on this one we have positives. Okay. And in this case we have a positive and a negative. So we add those two together and we end up with an attraction. So in this situation the rod will move away, and in this situation it will turn towards. Now that you've seen the demonstration, I would like you to prove that you understand what the demonstration showed you. So, answer the following to test your understanding. Number 1. In terms of electrons, how do the objects become charged? Number 2. Static electricity exerts a non-contact force. Explain why what you saw can be described as non-contact. Number 3. What happens when objects with the following charges are brought close to each other? Positive and positive, negative and negative, negative and positive. Pause now, have a go at these questions. When you're ready to move on, press play. So let's check your answers. Question 1. In terms of electrons, how do objects become charged? Well, during the rubbing, electrons are transferred from one material to another. The material that loses the electrons now has more protons than electrons, so is positively charged overall. The material that gains electrons now has more electrons than protons, so is negatively charged overall. Question 2. Static electricity exerts a non-contact force. Explain why what you saw can be described as non-contact. The materials do not need to be touching to feel the force of attraction or repulsion. And finally, question 3. What happens when objects with the following charges are brought close to each other? Positive and a positive will repel. A negative and a negative are like charges also, so they will repel. Negative and a positive, however, will attract. Now we're going to take a look at another method of transferring charge. The first method, you started with two non-charged objects and they gained a charge each. In this situation, we're taking a look at a charged object and seeing how we can transfer the charge from that object to something else by making contact. For this, we're going to use the fun fly stick, and I'm going to hand over to my colleague, Gandamp.
So now I'm to show you some real Middle-earth magic. What I have here is a special wand. With this wand I can bring metal to life. Here is a lifeless butterfly. With one wave, I bring it to be living. How? Inside this fun fly stick is a belt. The belt moves and the belt gets charged. As the belt is charged
With a positive charge,
the foil touches the belt and gains positive charge itself. This means that all of the surface of the foil is now the same charge, and like charges repel, so the foil will spread. And once again, it has lost its life.
Now that you've seen his bit of magic, now let's see if you've understood. Understanding check. Complete the following tasks to ensure you understood the demonstration. Number 1. Explain the interaction between the fun fly stick and the butterfly. That is in terms of charges. And number 2. Explain why the butterfly spreads out. Pause now. Have a go at this task. When you're ready to move on, press play. Now let's check your answers. The fun fly stick and the foil butterfly have the same positive charge, and so the butterfly will be repelled from the stick. The foil butterfly spreads out because the charge is spread across the surface of the foil, and so each part of the foil repels each other part of the foil. Another method of charging by conduction is touching one of these things. This is a Van de Graaff generator. I'm going to hand over now to Gandamp, who is going to show you what the Van de Graaff generator does.
So here we have a Van de Graaff generator. Here we have a metal conducting spherical dome. And here we have a belt that is rotated about a motor, and drawn off the belt here are electrons. This makes the belt overall positively charged, and then that positively charged belt draws electrons from the dome, making the dome also positively charged. Bear in mind, although it's plugged in, it doesn't mean that the electricity that you'll see is being drawn from the mains.
That's a good point that Gandamp made there at the end. The electricity that you see accumulating on the dome is not made from the mains electricity directly. All that the mains does is power a motor which turns the belt. You can actually turn the belt manually. So now that you've seen that, I wonder what happens if Gandamp would touch the dome without touching the floor, not allowing any direct pathway from the earth to the dome.
Let's see if we can find out. I can feel the hairs on my hands start to stand on end. I can see parts of my hair start to stand on end. Let's give it a little bit of a shake, shall we? So you see my feet aren't connected to the floor, so I am now having all the electrons, well, not all the electrons, but some of the electrons removed from my very being through the Van de Graaff, leaving me positively charged. And as long as I don't make an electrical connection, I will remain positively charged. Give it a shake. Loosen. Loosen those follicles! Loosen them! You shall not pass unless you loosen those follicles! Lovely.
Now that you've seen that, I would like you to try the following. Here is my Elsa doll. I've put my Elsa doll in a can on top of the Van de Graaff generator, as you do. I would like you to explain what you think will happen when I turn on the Van de Graaff generator. Pause now, write your answer. When you're ready to move on, press play. Okay, now it's time to check your answer. Watch the video, correct your answer if necessary. As we know, a positive charge will build up on the dome of the Van de Graaff generator. As it's in contact with the can, a positive charge will be passed to the can, and in turn a positive charge will be passed to the doll. So your answer might look something like this. Positive charge builds up on the hair. This is because the doll is insulated from the ground, so the charge can't easily leave the doll. Each individual hair has the same charge, and so they are repelled from each other and spread out. The key to this is that this is a build-up of what we call static electricity, and in order for this to work, we need the doll to be insulated from the ground. What do you think would happen if the doll wasn't insulated from the ground? Pause the video now, write down your thoughts, and when you're ready to move on, press play. So let's find out. I'm going to use the discharge stick to create a connection to the ground. And if you take a look, as I allow the charge to leave the dome, the charge also leaves the doll. As the doll's hair is an insulator, it doesn't flow very easily, so it takes direct contact from the discharge stick in order to remove the final bits of charge. Now you've checked your answer, that's the end of the presentation. However, if you'd like to try some experiments at home, perhaps you could try these, if you have a cat that is. Otherwise, stay on and I'll show you a couple of experiments that you can have a go at home. So here's a little experiment that you can try at home. Here I just have an empty can and I have a balloon. So all that I have to do is lie the can on its side, and if we just grab just a balloon and rub it on my head. So So the balloon now is getting charged. Hold it next to the can. And we should be able to make the can roll without touching it. Okay. Alternatively, if you don't have a balloon, just rip a piece of PVC pipe off the side of the house. I'm sure that your parents won't mind. So give the PVC rod a bit of a rub as well. And there we go. So that's something that you can try at home. And something else you can try at home is the same balloon next to a stream of water. Okay, so give that one a go yourself, see how far you can get the stream of water to bend. Thanks for watching.
Do not pay attention in this particular topic, and you shall not pass! Oh yeah, break me up.